12.6, we get a little exposure to 3D surfaces. In section 12.6, we're only covering 3D surfaces that fall into two categories. One category is called a cylinder, and the second category is called a quadric surface. But there's all kinds of other surfaces that you could make in 3D land that are not covered. It's just hitting on a couple of different kinds. Now, most of us, when you hear the word cylinder, we picture, you know, a Pringles can. That is an example of a cylinder. But the true mathematical definition is the one that is in your book and, you know, up on the paper here. A cylinder is any surface in which all lines that are parallel to all lines that are parallel to a given line and pass through a given plane curve. If you, like, so for example, here's the traditional cylinder. I could make a bunch of lines that go down the surface of this, and they would all be parallel to each other. Okay, if I make a line here, it's parallel to the line I make here, it's parallel to the line I make here. So basically, picture taking that shape and then doing anything you want with it. It's still going to have the same topological beginnings as the cylinder. So picture being able to take a piece of paper and bend it, and any surface that you can make by bending a piece of paper, not folding it, not doing origami with it, but just bending it would fit the definition of a cylinder. Okay, so you could make a sine wave with it, you could make a parabola with it, you could make, you know, something that was kind of like an exponential curve with it. So picture taking a piece of paper and any kind of bending surface that you can make with it fits the definition of what an actual mathematical cylinder is. It's just commonly this is a shape that gets used a lot, and so it kind of got a generic name, kind of like Kleenex. You know, people call Kleenex Kleenex even if it isn't really the brand of Kleenex, okay? So that's kind of like, this is a cylinder, but there's all kinds of other cylinders. So examples in your packet of those kinds of curves, you actually have to skip down. Like, these would be examples of cylinders. And so notice that their equations, of course you could tilt it and then that would bring the z in, but I mean I've given you a couple of basic ones like y equals e to the x. If you sliced it in the xy plane, you would get the shape of e to the x. But z is not listed, meaning z could be any value. And so this is stretching out. I know this is turned around funny because the software that I use turned it around funny. But your z-axis is here if you look carefully at how that's labeled. Okay, so it's stretching, the piece of paper is sort of stretching out the z-axis. The shape of the function, e to the x, is in the xy plane. Here's the same shape, but we use the formula z equals e to the y. It's stretching down the x-axis. And so we still get the exponential function shape, but it's in the yz plane. So the trace or the contour in the yz plane is the exponential function z equals e to the y. Okay, so those are examples of some cylinders. Again, picture a piece of paper and bending it. Any shape that you can make with a bent piece of paper is an example of technically what a cylinder is. And so it's formulas that make cylinders, one example would be writing a function but that has only two variables in it, but interpreting it in 3D. So I happen to use y is e to the x, but if you write, any function in two variables, but interpret it in 3D, then what's going to happen is the third variable can be anything, and so the shape of the curve of the function is just going to stretch out in the direction of, in this case it was the direction of z, it's stretching out in the direction of x. So you could do the same thing, you could graph, a parabola and it could stretch out. That's a way to make a cylinder with formulas. So here's another one. Notice x is missing, so the graph stretches out in the x direction. Again, the software that I use to print these, it kind of arbitrarily made its own axes and wouldn't let me change them. So I know they're kind of oriented in different directions than what we are used to. So here's the x-axis where we normally see the z-axis. So notice the curve. The curve is this hyperbola, and that hyperbola shape is stretching out in the x direction, making a shape that you can make with a piece of paper. So notice the next example, we have z equals cosine of x. So y is left out, and with y being left out, we have the wave, the cosine wave, stretching out in the y direction. So here's my wave. That wave is being stretched out in the y direction, creating what is technically a cylinder. And you can see the parallel lines here. This is a good indication of the lines that you can make on the surface that are parallel to each other. At this stage, I don't want to get into it because how to actually really graph such a thing is better in that parametric form. Remember, we talked about, you can trace a surface with a parametric equation, but if I take a cylinder, if I stretch it up the z-axis or the x-axis or the y-axis, the formula is going to be very simple. If you tilt it in space, then the formula does get more complicated. It's still a cylinder, but writing out the formula gets more complicated. And the same would be true for any of these other shapes. Like I could take those shapes and I could tilt it in 3D space. How to represent that exact surface gets more complicated when you tilt it. And really the best way to end up graphing it is with parametric. So I don't know if you remember back to the day that I was showing you that guy came up with how to graph different shapes of noodles. And if you looked at those formulas, they were pretty complicated, but all of them were parametrics. So you were tracing x separately and y separately and z separately and then putting it all together to get the surface. So the more complicated your surface gets, you're able to handle that by worrying about x and y and z separately. But for right now, in the ending of chapter 12, your book just kind of sticks to basic cylinders that you can represent without having to get into the complication of the parametric equations. Okay, so that's why, they're giving you examples and I'm kind of following their lead. You can create cylinders by making up some function, leaving out one of the variables. The variable that gets left out is the direction that the shape stretches out in. So that one software, why don't we make a couple other examples?